Welcome to the session on Maxwell's equation inside matter and boundary conditions. So, in the last session we have seen that the Maxwell's equation, and now we are going to rewrite this Maxwell's equation in matter, because when we apply electric and magnetic field to matter, it undergoes polarization and there will be accumulations of bound charge or bound current, but we do not have any direct control over which the bound charge or bound current. So, that is the reason why we are rewriting this Maxwell's equation in terms of free charge density or free current density and bound charge or bound current density. We have some direct control only over the free charge or current density. An electric polarization P results in an accumulation of bound charge, and the value of rho b is given by minus del dot P, where P is the electric polarization. Similarly, a magnetic polarization M results in an accumulation of bound current and is denoted by JB, that is equal to del cross M. So, these are the situations we have already seen in electrostatics and magnetostatics. Now, we are going to see whether any bound charge or bound current corresponds to change in electric polarization. To understand that, we consider a tiny chunk of material. To that material we are applying an electric polarization. When we apply polarization or electric field to this material, it undergo polarization and a charge density sigma b is collected at one end and minus sigma b is collected at the other end. Now, we keep on increasing the polarization or we keep on changing the electric field. Then what happens? Here P is in this direction. So, when we change electric polarization, sigma b moves a slide to the right and minus sigma b moves a slide to the left. That is, there is movement of sigma b or the movement of charge density associated with this surface, or surface charge density moves a bit when we change the electric polarization. But the movement of charge is termed as current. That means, when we change the electric field across it, the surface charge density moves a bit or it contributes a current. That current, in order to measure that current, we measure dI. So, what is dI? It should be equal to whatever be the change in sigma b with respect to time, because when we keep on changing electric field means it varies with respect to time. So, sigma b moves a bit to the right or plus sigma b moves a bit to the right means sigma b changes with respect to time. So, dI is equal to del sigma b by del t into dA perpendicular, because the charges are moving only on the surface end, because in between all the dipoles cancel away and the remaining charges are concentrated on both the ends. So, dI is equal to del sigma b by del t into dA perpendicular, but here we are taking sigma b is equal to P. So, we are replacing sigma b by P, that is del P by del t into dA perpendicular. Then we are taking this dA perpendicular to the left side, that is dI by dA perpendicular is equal to Jp, because we have already defined J as the current per unit area perpendicular to the cross section. So, here we have dI by dA perpendicular, that means that is volume current density. Then here the subscript we have shown this P just because this surface current density arises because of the change in electric polarization. So, dI by dA perpendicular is equal to Jp is equal to del P by del T from this expression. Now, we are going to check whether this polarization current density, that is Jp, satisfies equation of continuity, because equation of continuity is the mathematical statement for the conservation of charge. So, we have to know from where this current flowed out. For that, we are applying del on Jp, that is del dot Jp, or the divergence of polarization current density, that is equal to del dot, we substitute the value of Jp, Jp is nothing but del P by del T. So, del dot del P by del T. Now, we take this del inside because this is a operator, it acts on a vector that is P. So, del by del T of del dot P, rho B is equal to minus del dot P. Now, we have del dot P. So, we can replace this del dot B by minus rho B, that is del dot J P is equal to minus del rho B by del T, that is J P or polarization current density satisfies the equation of continuity, that is del dot J P is equal to minus del rho B by del T. That means, polarization current density is necessary to conserve the bound charge, because some of the bound charge flows as polarization current density. Now, we are going to rewrite the charge density and current density in terms of free and bound. So, rho is charge density. We know one more types of charge density, that is bound charge density. So, we split rho into two, that is free charge density and bound charge density. Then we substitute the value of rho B. Rho B is nothing but minus del dot P. So, rho becomes rho F minus del dot P. J as free current density, bound current density and polarization current density, or we can say that J is Jf plus Jb plus Jp, and we substitute the value of Jb and Jp, that is Jf plus Jb is del cross M and Jp, that is due to a change in electric polarization, that is del P by del T. Next, we can think whether there is any charge or bound current, charge or current due to change in magnetic polarization. That means, if we keep on changing magnetic polarization, there will be any contributions to J or rho, but we can see that del cross M is equal to Jb, and whatever be the change in magnetic polarization, it will be automatically come to Jb. That means, change in magnetic polarization does not contribute anything to charge or current density. So, J is equal to Jf plus del cross M plus del P by del T. Now, we are rewriting the terms containing rho and J in terms of these expressions. In Maxwell's equation, only in two equations there is rho and J. So, first one is Gauss's law. So, initially it is given by del dot E is equal to rho by epsilon 0. So, del dot E is equal to this rho we are replacing by rho F minus del dot P. So, that is 1 by epsilon 0 into rho F minus del dot P, or we can write, we are taking these two terms to the same side. For that, we are multiplying this epsilon 0 to this side. So, del dot epsilon 0 E plus, because we are taking this term to the left side. So, minus del dot P becomes plus del dot P. So, del dot epsilon 0 E plus P is equal to rho F. Now, we label this quantity, that is epsilon 0 E plus P, as D, which is known as electric displacement. So, that is del dot D is equal to rho F. So, inside matter, Gauss's law becomes divergence of D is equal to rho F or free charge density. So, inside matter we can rewrite Gauss's law in this form, that is del dot D is equal to rho F. Next, we can see what is the form of modified Ampere's law in matter. Initially, it is given by del cross B is equal to mu 0 J plus mu 0 epsilon 0 del E by del T. Here we are replacing this J by Jf plus Jb, that is del cross M, plus Jp, that is del P by del T, plus the same thing, that is mu 0 epsilon 0 del E by del T. Now, we are taking the curl of equations on to the left side, that is we are taking del cross as common, then we are dividing this equation throughout by mu 0. So, 1 by mu 0 times b minus, because we are taking this del cross m to the left side. So, del cross is common. So, 1 by mu 0 b minus m is equal to what is remaining, j f and del p by del t, that is j f plus del p by del t plus mu 0 epsilon 0 del E by del t is there, and we are collecting it together. So, it becomes del by del t of epsilon 0 E plus p. Here we have del by del t, we divide this equation throughout by mu 0, that means this mu 0 goes and this mu 0 also goes, and remaining we have this term and this term. Here we have taken del by del t as common. So, this is epsilon 0 E plus this term p, and we have defined epsilon 0 E plus p as d. So, this expression becomes del d by del t. So, modified Ampere's law becomes del cross of 1 by mu 0 b minus m is equal to j f plus del d by del t. Now, we label this expression, that is 1 by mu 0 b minus m as h. So, the modified Ampere's law becomes del cross h is equal to j f plus del d by del t. So, inside matter, modified Ampere's law becomes, that is this equation becomes del cross h is equal to j f plus del d by del t. So, we can see that in terms of free charge and free current density, we have expressed the Maxwell's equations inside the matter. That is, first one is del dot d is equal to rho f, that is the form of Gauss's law inside matter. Second one, there is no change, it is independent of rho and j. Third one also there is no change compared to inside matter and outside. But the fourth one becomes del cross h is equal to j f plus del d by del t. Now, we are going to see what happens to these Maxwell's equation when we cross a boundary. That means, we have two media, when we move from one medium to another medium, what happens to these quantity, that is E, B, D and H, whether they are continuous or whether they are discontinuous. So, here we have two options, either we can move from one medium to another medium, or we can move through one medium itself, but in between we have a plane sheet, it is having surface charge density or current density. In that situation also, actually we are crossing this sheet having surface charge density or current density. Now, here we have rewritten the Maxwell's equation inside matter in integral form. So, that is surface integral d dot dA is equal to q f enclosed, and surface integral b dot dA is equal to 0. Then integral over closed loop E dot dl is equal to minus d by dt of surface integral b dot dA, and last one, that is modified Ampere's law becomes integral over closed loop h dot dl is equal to I f enclosed plus d by dt of surface integral d dot dA. Now, we can check the first equation, that is integral form, that is integral d dot dA is equal to q f enclosed. We can check, we can apply this equation to two media. Here we can see that a plane sheet is there, and the plane sheet is having a surface charge density sigma, and we have two medium, one above the plane sheet having charge density and the other medium is below the surface. So, here this 2 is below the plane sheet and one is above the surface. Then when we move from second medium to first medium, what happens to the quantities of d1, whether they are continuous or discontinuous, that we are checking. So, in order to apply the Gauss's law in matter, we need a closed surface, because it is defined as integral over closed loop d dot dA is equal to QF enclosed. For that we are choosing a Gaussian pillbox. Here you can see that surface just like a matchbox. So, here we are extending this matchbox or Gaussian pillbox on both sides of the surface. That is, suppose this is the plane sheet having surface charge density sigma, then we consider a Gaussian pillbox in such a way that half of the portion moving on the upper side of the surface and half of the surface moving in the downward portion. So, here this dotted portion shows the portion of the Gaussian pillbox which is lying under the surface charge density or the sheet, and this surface it is above the sheet having surface charge density sigma. Now, we have to apply this Gauss's law over the entire loop. You have to integrate over the entire area, that means up area, down area and the side areas also. But here we have taken a Gaussian pillbox in such a way that the width of the pillbox goes to 0. That means the Gaussian pillbox is just grazing over the surface. So, we can take the contributions of d dot dA. Here this sheet is having surface charge density sigma. This is positive. That is the reason why field is always pointing outward, whether it is upward or downward, it is always pointing away from the surface. So, on the top surface d1 is pointing in the upward direction. Here the direction of area vector we have chosen it as upward direction. So, when we project d1 over the area, both are the same direction. So, d1 dot A, that is the first contribution, then we are projecting d2, that is downward, that is acting in the downward direction. So, but d2 is acting in the downward direction, but area is acting in the upward direction. So, d2 dot A means it will give d2 dot A, that is d2 A cos 180, that is negative. So, that is the reason why d1 dot A minus d2 dot A is equal to, there is no contribution from these sides, just because I told you that the width of the Gaussian box tends to 0. So, these sides do not contribute anything. So, integral over closed loop d dot A means we have to take the contribution from upside, downside and all the sides, but these sides will not contribute just because the width of the Gaussian pillbox goes to 0. So, d1 dot A minus d2 dot A is equal to QF enclosed. What is the charge enclosed over this area? Here the area of the pillbox is given as A. So, of course, the total charge enclosed in the surface is the charge density times area. Here sigma is surface charge density. So, QF enclosed is sigma F into A. Here area is common. So, we can cancel, remaining is d1 dot A means we are picking the component of d1 along the direction of area. So, this component is perpendicular to the surface, because here we have a surface like this horizontal and we are picking d1 dot A along the vertical direction. That is the reason why we are choosing this as perpendicular. d1 perpendicular minus d2 perpendicular, that means d1 perpendicular means the perpendicular component of d in the first medium, d2 perpendicular means the perpendicular component of d in the second medium, because I told you that this plane sheet having surface charge density sigma separates two medium, one above and the other one below. So, d1 perpendicular minus d2 perpendicular is equal to sigma times free charge density or whatever be the charge density enclosed in that sheet. It is very clear that because some field is passing from the downward and when it moves to upward direction, there should be contribution from whatever is coming from the from the downward plus the contribution due to the plane sheet. So, of course, the field in the upside and downside are not same, it will be discontinuous by an amount of the charge density. So, perpendicular component of electric field suffers a discontinuity when it crosses a plane sheet having surface charge density sigma. So, this is the plane sheet and field is coming from here and going to this side. So, when it reaches the upward, there should be contribution from whatever is coming plus the contribution due to the plane sheet. So, the discontinuity will be the whatever be it's due to the plane sheet, that is sigma f. The same next we apply that integral over closed loop B dot dA is equal to 0 to the same loop. So, we will get B 1, that is the magnetic field over the first surface. Here right side is 0. So, B 1 we are projecting on the area A minus B 2 we are projecting over the area A. Here also the negative side comes because we are defining the direction of area in the upward direction. So, that is equal to 0. So, we have chosen the component of magnetic field along the direction of area, one in medium 1 and the other one in medium 2. So, B 1 perpendicular minus B 2 perpendicular is equal to 0. Here A is common. So, we can see that perpendicular component of electric field suffers a discontinuity when it crosses a plane sheet having surface charge density sigma, but nothing happens to the component of magnetic field. Next we are going to apply that equation 3, that is integral over closed loop E dot dl is equal to minus d by dt of surface integral B dot dA. This is our Faraday's law, that is del cross E is equal to minus del B by del T. We have expressed it in terms of integral form. So, integral over closed loop E dot dl is equal to minus d by dt of surface integral B dot dA. In order to apply that Faraday's law, we need a closed loop. So, for that we choose a closed Amberian loop here. This is the Amberian loop, and here we have a plane sheet having surface current density. So, here there is some source of magnetic field is on the plane sheet, or some current is flowing over the surface, that is K, and we know how K is defined, that is the current per unit length perpendicular to the flow. In order to apply this Faraday's law, we have chosen an Amberian loop. So, here the Amberian loop direction is like this. We are moving in clockwise direction over the loop. So, this is the direction of K, and so L is the length of the loop that is taken in this direction, that is towards right. So, this portion is below the plane sheet having current density K, and this portion is above the plane sheet having current density K. That is, this plane sheet having some surface current density, and the current is flowing over this surface, and we are choosing an Amberian loop perpendicular to the surface. So, part of the Amberian loop lies upward and part of the Amberian loop lies downward. So, E 1 dot L. So, we are projecting E 1 over the length of the loop here, because we need E dot dl over a closed loop. That means, we need the contribution of E over the entire length of that loop. Here we are projecting towards this direction, that is E 1 dot L. Then this side we do not get any contribution, because we have taken the assumption that the width of the Amberian loop goes to 0. That is the reason why this side we will not get any contribution, because length goes to 0. The downward we are getting E 1, but we are projecting on the just opposite direction, because here we have taken dl along this direction. So, this direction means minus L. That is the reason why E 2 dot L becomes negative. Then again over this length we do not have any contribution, because the length or the width of the loop goes to 0. That is equal to minus d by dt of surface integral B dot dA. Here there is source for B, that is surface current density, but we are projecting over an area, that is dA. dA is the area of this Amberian loop. This Amberian loop is having some length, but the width goes to 0. That means, dA goes to 0. So, the right side becomes 0. So, E 1 dot L. E 1 dot L means we are projecting E 1. So, here the Amberian loop is like this. So, we are projecting on L, means we are having the horizontal component. So, that is the reason why E 1 parallel, the component of electric field in medium 1 in parallel direction, E 1 parallel, minus E2 dot dl means we are taking the projection of E2 over the length, but in the second medium. That is the reason why E2 parallel that is equal to 0 because dA goes to 0, that we have taken the width of the loop tends to 0. So, E1 parallel minus E2 parallel equal to 0, that is the parallel component of electric field does not suffer any discontinuity when we take it over a plane sheet having surface current density, because we know that surface current density is not a source of electric field. Next we can apply equation 4, that is modified Ampere's law to this Amperian loop, that is given by integral h dot dl is equal to if enclosed plus d by dt of d dot dA. Here this portion goes to 0 because of the assumption that the width of the loop goes to 0. So, the area term goes to 0. So, we do not have any contribution from this term, and we will have contribution only from this term, that is if enclosed, whatever be the current enclosed in that Amperian loop. So, we are integrating over a closed loop. So, we have to move through this loop. So, this is the plane sheet and this is the Amperian loop. So, we have to integrate over the length. So, first we are integrating on the upside, and this side will not contribute because the width of the loop goes to 0, but downward it will contribute. So, here we can write it as h1 dot L minus h2 dot L is equal to if enclosed. Here there is no contribution from these two sides. Then here this term becomes negative just because we are taking the upward direction of length. This as positive means of course this moment should be negative. So, h1 dot L minus h2 dot L is equal to if enclosed. But here we have the plane sheet having surface current density Kf. So, we have to express this if enclosed in terms of surface current density. So, here Kf is acting in this direction, or K surface current density is flowing in this direction, and we are having an Amperian loop perpendicular to surface, and we need to find the current passing through this Amperian loop, that is this Amperian loop. For that we define the direction of n, that is n is a unit vector pointing in the upward direction and L is in this direction, that is towards right. So, n cross L. So, we turn a screw from n to L, that means n cross L will advance in this direction, or n cross L is in the same direction of Kf. So, to get the if enclosed, that is current passing through this loop having length L, we know that Kf is current per unit length perpendicular to the flow, but we need the current passing over a length L. That is the reason why we are taking Kf dot n cross L is in the same direction of Kf. So, Kf dot n cross L, this is unit vector times whatever be the length of that Amperian loop. So, Kf dot n cross L into L. Here we just rearrange this dot and cross, or we interchange the position of dot and cross. So, Kf cross n dot L. So, our initial equation becomes h1 dot L minus h2 dot L is equal to Kf cross n dot L. That is, initial equation was h1 dot L minus h2 dot L is equal to if enclosed. We have substituted the value of if enclosed, that is Kf cross n dot L. Then all these we are projecting over the length, that means over this surface, over this side, or over this side. So, this contribution or this contribution compared to this plane sheet means parallel component. That is the reason why h1 parallel minus h2 parallel equal to Kf cross n. Here L is common in all the terms, so we are cancelling it. So, we get the parallel component of magnetic field suffers a discontinuity when it crosses a plane sheet having current density Kf, and the amount of discontinuity is given by Kf cross n. So, we have seen that when electric field or magnetic field crosses a plane sheet having surface charge density or surface current density, only one component of D and parallel component of magnetic field surface a continuity, and here we have just rewritten that equation for a linear media. For a linear media, D is equal to epsilon times E and H is equal to 1 by mu times B. Initially we got it as D1 perpendicular minus D2 perpendicular is equal to sigma f. So, here we substituted for linear media D is equal to epsilon times E. So, epsilon 1 E1 perpendicular minus epsilon 2 E2 perpendicular is equal to the amount of surface charge density, and this equation there is no change, that is E1 parallel minus E2 parallel is equal to 0 and B1 perpendicular minus B2 perpendicular equal to 0, and this initial equation was like this: H1 parallel minus H2 parallel is equal to Kf cross n, but H is equal to 1 by mu times B. So, H1 means 1 by mu 1 B1 parallel minus 1 by mu 2 B2 parallel is equal to Kf cross n. Here mu 1 and mu 2 are the permeabilities of these two media, whereas epsilon 1 and epsilon 2 are the permittivities of these two media. So, the property entirely depends upon the medium or the values of epsilon and mu. So, we have, it is clear that when electric field and magnetic field crosses a plane sheet having surface charge density sigma or volume current density surface current density K, it suffers some discontinuity and is given by D1 perpendicular minus D2 perpendicular is equal to sigma f, or we can write epsilon 1 E1 perpendicular minus epsilon 2 E2 perpendicular is equal to sigma f, or 1 by mu 1 B1 parallel minus 1 by mu 2 B2 parallel is equal to Kf cross n. Let me conclude with this. So, we discussed about the Maxwell's equations inside matter. In that we have rewritten all the equations in terms of free and bound charge densities plus free and bound current densities. Then we have applied these equations over a plane sheet having surface charge density and surface current density. Reference for this section is Introduction to Electrodynamics by David J. Griffith. Have a look at it and try to solve all these things. Hope that you had a good time with me. See you on next time. Till then, bye.